In order to download LTSpice, what you do is just Google LTSpice, and the first link whatever you get, you click on that. So LTSpice is a free software platform that you can use for simulating analog circuit, and it is by a company called Analog Devices, which is a very popular company, and this software is also very popular now. And depending upon your system, whether it is Windows or Mac, you can click on it and download it. I have already downloaded it, so and then click on it further and install it, depending upon your system, whether it is 64-bit system or 32-bit system. It will not take much time, and after installation you will have this icon. You can have this shortcut, and if you double click on it, it will open up like this. Okay, LTSpice 17. It is written 17, LTSpice 17. So how many of you are with me? If you have installed, can you open up and let me know that you have taken this page? And then if you are not responding, I will just proceed. You take new schematic. So this is like a place where we connect components and wire up the circuit, just like we did in Logisim. There we connected logic gates, multiplexer, those kinds of digital blocks. But here we will take discrete components like resistor, capacitor, diode, etc., and we will connect them. Okay, so first of all, let us do say half-wave rectifier, what we did yesterday. So what are the components that we require for it? We obviously require a diode. You click here, bring the diode, and then right click. You can choose the next component. We require a load resistor, so I am choosing a resistor. If you again click left, then repetition of the same component will happen. So in order to avoid it, you click right, that will disappear. So in a half-wave rectifier, we need a diode, we need a resistor, then we need a voltage source. To take the voltage source, you click on this icon which is written component, and you go for voltage, so you can get voltage. So this is a voltage source, and then click OK. You get that. We want to give, say, a sine wave, and then we need to have a reference in any circuit simulation. So this is the reference or ground, so that also you take. Okay, so now if you want to rotate it, what you need to do is you go to this icon which is written move, click on that, and then bring it on the top of whichever component you want to rotate. Click one more time, then apply Control R. Okay, you one time when you apply Control R, it will rotate by 90 degree. If you apply 2 times, 180 degree. If you want 3 times, then 270 degree. So depending upon whatever way you want to place it, you rotate it, and then wherever you want to fix, you move it and click one more time, it will be fixed there. So similarly you can shift this also, and now you need to connect them. So you go to this wire icon and click on it, and then you see that a cross sign will appear. Bring that cross sign wherever you want to start the connection. Click there, draw wire, click wherever you want to turn, and then click wherever you want to end. Same thing you repeat, click wherever you want to start, turn, end. Again, start, turn, end. Similarly, you need to connect the reference. So if you are doing practically in the lab, then this will be like your ground. CRO will have a ground, your circuit will have a ground, your power supply will have a ground. All this ground should be connected together. So again, start, end. Alright, so we made the circuit connections. Now we need to specify the value of resistor. So if I want to get out of this wiring mode, you right click, and then that will go, and then bring your cursor on the top of the component whose value you want to assign. So you will get this hand symbol. So you right click after getting the hand symbol, then say 1 kilo. So if you want 1 kilo ohm, you write 1K, and then diode, either you can just leave it as such, or you can, if you want a particular diode which you corresponding to the component that you use in the lab, again bring the hand symbol on the top of the diode and right click, and then pick whatever component that you want to assign. The silicon diode usually start with this 1N. Okay, so 1N is a silicon diode, and then there are some versions of silicon diode like Schottky silicon diode, etc. So you can see here the type. So these are components which you can buy from market. So the models are available here, and so let us so this is like a 4004 is something very popular, or this is a similar one. The difference is that different diode will have different cut-in voltage, breakdown voltage, so those details, reverse saturation current, but it is all incorporated in a model file here. So every component will have a model file. You click OK, so that component will be assigned here. Similarly, we need to specify what is the input wave. We need a waveform, not a DC voltage. So you right click after getting the hand symbol. If it is a DC voltage, you directly give here whatever is the DC voltage you want to give. But if you want to give say sine wave, what you do is go to the advanced. We need a sine wave because we are doing rectifier. The power line that is coming to our house from ASEB is basically giving us a 50 Hz sine wave. Standard amplitude is some or RMS value is 230 volt. So 230 into root 2 will be the peak amplitude. Okay, so you don't need to give the same value. Just for our study purpose, you can give any value. Say let's give an amplitude of say 10 volt, and the frequency in the power line it is 50 Hz, but I will give 1 Hz. So that those are values that I am giving in order to make our analysis simple enough to visualize. Okay, so now I specified the sine wave. Its amplitude is 10, its frequency is 1 Hz, resistance is 1 kilo ohm, and I have a diode which is a component I1N4148. Alright, the next step is to start simulation. So you have to go to this run icon. You can see the picture of someone running here. So click on it. It will ask you what type of analysis you want to do. Then okay, you can choose transient. Transient is what we will use. Transient is basically plotting the value of voltage or current with respect to time. Okay, so since I have chosen 1 Hz frequency for the source, I would like to see the waveform say for 3 cycles. Okay, so let me write it as 3 second. Okay, 3 second is what I want to run the simulation. So similarly, there is a command here, dot tran 3s. Okay, so I click OK. So now a waveform plotting window will open, but nothing is plotted so far. Now you need to decide what you want to see. So for that, you take this cross symbol, move it in the circuit. You will see if you want to measure voltage at a particular node, this change of cursor will happen when you touch the point, and then you click there. It will give you the waveform for 3 seconds, because we have specified 3 seconds, so there will be 3 cycle because I have taken 1 hertz frequency. So that's the voltage which will be coming for 3 seconds at that particular point, which is basically the input voltage, the voltage at this point with respect to the reference. So that is the voltage across the source, voltage source. So some name is given here, VN001. Now we also want to see what will be the output voltage at the output, which is the voltage across the resistance. So you bring the cursor again there, again click there. So here it is, your output has come. All the positive cycle will remain, all the negative cycle is removed. So you can see that. And you can also see something, the positive cycle is not exactly following the input positive cycle. The negative cycle is completely cut off and the positive cycle is not exactly following. There is a slight discrepancy. I guess you have understood that from yesterday's class. Can somebody tell me what is the reason why the peak at the output is not exactly same as the peak of the input? Can you tell me, somebody?
Sir, cut-in voltage.
Cut-in voltage. So you have to subtract the cut-in voltage. So 10 minus whatever is the cut-in voltage of this. Okay. So, and if the amplitude of the input voltage is very large, the difference will be observed very negligible. So if it is less, the difference will be more pronounced. So 10 is somewhere okay to neglect, but let's see what will happen if I change. So this voltage, say to 1 volt. Okay, and I run this simulation again. I plot the input. Now I should get 1 volt. Okay, as you can see in the waveform, amplitude is 1 volt. Now if I plot the output, you will see there is so much difference. You see, the discrepancy is very pronounced. That's why I said it's not a good approximation to take the diode to be ideal when the input voltage levels are small. Okay, so here you can also see what or measure actually what is the cut-in voltage. The difference between the two peaks, that is the cut-in voltage. So in the conduction angle is also much less, right? Just like yesterday we calculated one problem, it came out to be 1/3. So this is similar. Now if you want to know the current, so conduction is happening only during the time for which the output is shown, because current is basically multiplied with the resistance to get the output. So the current waveform should be looking similar to the output waveform in this particular circuit. So to get the current, you can move the icon or the cursor, and if you place it over any component, you can basically notice a change where it shows a current symbol. So if you click, you get basically the current waveform. Now on a voltage scale, you cannot see the magnitude of current. So what happens is that the moment you show current, on the right side there is a new scale that appear, which is calibrated in terms of microampere or ampere current units. The left side, the units are voltage units, and x-axis is same, it is the time. Independent variable is time, variations are with respect to time. So if you look at here, current is somewhere like 400 microampere. Now you can calculate this current roughly. There is a 0.7 drop at or I think 0.6, right? If you look at the difference, it is 1 minus 0.4, so it's around 0.6 for this particular diode. So 1 minus 0.4, that is so you have a voltage of 0.4, and 0.4, if you divide it by 1 kilo ohm, voltage divided by resistance, that should give you the current. So 0.4 divided by 1 kilo ohm, that will be 4 into 10 raised to minus or you can say 0.4 milliampere, and 0.4 milliampere is same as 400 microampere. So yes, the values that the graph is showing is matching with whatever we have calculated manually. Okay, now is there any doubt with respect to this? This difference will be pronounced when the input voltage is less. Now you can also check whether what will happen if we change the input voltage, say lesser than 1. Say for example, if I take 0.5, then what is going to happen? Okay, so if I take 0.5, my amplitude is now 0.5 or 500 millivolt, which is same as 0.5 volt. Now what do you think will be the output if I check the output? Can anybody guess? Before I show it, can anybody tell me what is going to be the output? If you have followed me, you should be able to tell this.
Sir, nothing.
Okay, let us check it. Yeah, almost nothing. There is a slight peak which is very, very negligible. That means the current is not really zero, even when we say cutting voltage is 0.6. So at 0.5 also there is a slight amount of current, and because the resistance is big, it is creating a voltage. So,
Sir,
right.
in this diode D1, what is the cutting voltage, sir, in this diode 1 and 4, 4148?
Yeah, so that's what I told you. We found it as 0.6, right? If when I did it with 1 volt, we could measure that. So if I put it back as 1 volt, okay, and then run it again, so you can measure it. This is how we experimentally measure the cut-in voltage. This is one of the way, and then another is you see the output. Okay, so the difference between the input and output voltage, if you take at any point, say at the peak, so if you look at here, this is like say how much, 0.4 and maybe a little bit, right? If you slightly, if you want, you can enlarge it to make yeah, it's above 0.4, slightly above 0.4 maybe, but it is less than 0.5. so maybe we can say it is 0.45. okay, the peak here is 0.45 and this is 1. So 1 minus 0.45, which is 0.55. So this difference is the cut-in voltage, the amount of voltage that will be dropped across the diode. Okay, is that clear? This is one way to find out the cut-in voltage.
Yes, sir.
Now other way you can find is you look at the manual, or if you just Google this component, okay, 4148 1N4148. So 1N4148, you Google cut-in voltage. It should give you, yeah. So see, what we have calculated is 0.55, right? So 4148. So this is the cut-in voltage. But cut-in voltage also depends upon the operating point. You can download the data sheet. So if you search for data sheet, so then you will get a document which will explain. It will be a PDF file. So 4148 itself has various versions. There is a simple 4148, then 4148D, G, L, etc. So there will be differences in each of this, and then there will be a PDF file. If you open the PDF file, so this is the PDF file. It will show lots of details. Its characteristics, temperature dependence. So any component data sheet is available. Reverse saturation current. So look at these and you will get a lot of details. More than what we usually require. You will get forward voltage. So this is the characteristics, but it is plotted in logarithmic range, logarithmic scale. Okay, so you can see the forward voltage is going in linear way, 0.3, 0.4, 0.5, 0.6, etc. And it is plotted by keeping the diode at different temperatures. 150 degrees Celsius, which is quite hot, 100 degrees Celsius, that is a boiling point of water, 25, that is room temperature roughly. Very cold region, you will get a different current. So current varies for the same voltage depending upon temperature. So those are like properties of semiconductor material. So forward current is given in milliampere, from 0.1 milliampere to 1000 milliampere, which is like 1 ampere. So it can take very high current also. So depending upon the diode, the thickness of this material, the device structure, the power handling ability, operating point, 200 milliampere at temperature 25 degrees Celsius, and it can be operating from minus 65 degrees Celsius to 200 degrees Celsius. So surge current maximum allowed is 2 ampere, surge current A, but with the power dissipation 8.3. So with the sine wave. For square wave the surge current is 1.41. so all this you can find out. Okay, so I just informed you all of this. Any other doubts with respect to this? Otherwise we will go to another, say, Clumper circuits. So you can save these files into a folder. Save as, you can open a new folder here, and then you can put your file there. Okay, now I have done few circuits. So this half wave rectifier I have already shown you. Now let's look at clippers. I think I gave you one exercise. I don't remember the voltage amplitude that I gave you. Let me check. Yeah. So this is what I told you. Create a circuit, Clumper circuit, which can give you this output from this input. So 6 volt peak to peak, and it is a triangular wave. Okay, let me see if triangular wave is available. Triangular wave. Pulse is there, so you can have square wave, exponential. So I don't see a triangular wave. Okay, so let us use sine wave itself. So it is only the shape that would vary. So amplitude I am giving as 6 volt. Frequency is not mentioned. Okay, 1 hertz I have taken. Then what is the output I want? I want to clip off anything above 3 volt. Anything above 3 volt. Now here also there is a diode. Okay, I have not specified what is the number of the diode, so if I want I can pick the diode. Again, let me use 4148 because we kind of know it is having a cut-in voltage of 0.65. So if I want the clipping to happen about 3 volt, I should give a appropriate battery voltage, so that after adding the cut-in voltage with the battery voltage I will get 3 volt. So can somebody tell me what should be the battery voltage I should give, so that after adding the cut-in voltage of the diode with the battery voltage I should get 3 volt. Cut-in voltage is 0.65 if you take, so I should give this as 2.35. So if I give 2.35 volt DC here with this polarity, then cut-in voltage is 0.65, so 2.35 plus 0.65, that should make 3 volt. So whenever the diode is turned on, it will give you 3 volt. Okay, so forward bias region is here, where it will give 3 volts. So I am aiming for getting this waveform. Alright, I put a 100 ohm because that should not matter much. Of course, yeah, in practice the diode also has some resistance, so if that resistance should not make much difference, so it is better to keep say 1k again. Okay, so Only difference is that I am using a sine wave because that is available here, but otherwise everything is same. So let us run it for 3 time periods. Okay, .tran 3, simulate. Oh, I have another window already open, so I don't want to keep both, so let me just close this and close this also. Let me do it again. Okay, so this is my circuit. I would like to see the 6 volt sine wave that is coming, and now my output, which would clip at 3 volt. Anything above 3 volt it should cut off, that is clipping. Yes, I got exactly the way I wanted. Here I am using a real diode, not an ideal diode. If it was an ideal diode, I would have used a 3 volt battery here instead of 2.35. But here I used a 2.35 volt battery because I know there is a cut-in voltage across the diode D1, which is 0.65. From the data sheet or from our calculation from the earlier experiment, we got that. So this is the way we handle. In the class I did not do any analysis using the real diode, but now I am telling you with the real diode, it has got a cut-in voltage. So when it is forward biased, there will be a drop of 0.65, and that drop may vary from diode to diode. So every diode may have a different cut-in voltage, so you need to take accordingly. So this is quite close. Okay, it's almost 3 only. Okay, we can accept it. So it has clipped off. So it's a wave shaping circuit. Whatever is the input wave. Now if you want to delete the input, you can delete this trace by right clicking, and you can just see the output. Okay, now so let us close this. Let's try to do the other problem. There is a second part to the problem. If you go back, the second part is like create a waveform like this. Now here the diode is forward biased for majority of the time, like until the peak comes. So maybe I should a little bit, if I am plotting it for 2 cycle, I should draw it more properly. During the second half cycle also there will be a peak like this. Okay, so this is 6 and this is 3 again. Now what should be the circuit for getting this waveform? Now so can somebody suggest? Anybody tried this problem?
So maybe we need to reverse the direction of the diode.
Okay, so let us try that. So if I take it out and then Control R, I have reversed that direction. Okay, so now if you look at it should be reverse biased above 3 volt, and it should be forward biased below 3 volt. So will this battery voltage will do that or not? Okay, so if you look at the picture, you see this is the forward bias. You are getting 3 volt, and 3 volt is because there is a forward bias drop of cut-in voltage 0.65. Okay, and 0.65. Added to that there is 2.35, so that will give you 3 volt. But if the input voltage is larger than 3 volt, then this diode will be reverse biased, and if it is reverse biased, whatever is the input waveform, that should follow. So it looks okay to me, and see whether there is any problem. So let us run this. Let us look at the input voltage. That's fine, and the output voltage. Yeah, it is not correct. What is wrong? It's not getting flattened at 3, it is going below 2. So can somebody tell me what went wrong with our assumption? What we need to correct?
So battery voltage.
Repeat, I couldn't hear.
So
battery voltage. Yes, battery voltage is not taken correctly. Okay, so right now it is basically 2.35. so let's see, when is this diode getting forward bias? This diode is getting forward bias when the input voltage is 2.35 minus cut-in voltage, right? 2.35 is the voltage on the P side. So when the N side voltage is cut-in voltage lesser than 2.35, right? So that is what? That is basically 1.7. That's what we are getting. So we need to calculate it properly. So this diode is going to be, if I want this diode to be forward biased at 3 volt input voltage, then what I need to do is I have to change this to, so somebody tell me what should be the DC value that I should give?
3.65.
3.65. So if I give 3.65, yes, when it become 3 volt, 3.65, right? So now it should work. So let's see this. You have this. Yes, perfect. At exactly 3 volt we have. So this is the idea. So you only need to check one thing: when does the diode get forward biased, and the voltage onward from that point where it gets forward biased, that voltage you need to find out. So you just need to look at what is the P side voltage, and then any voltage lesser by a cut-in voltage than the P side voltage on the N side will make the diode forward bias. When it is forward biased, you get 3 volt at the output. Okay. So here it is minus plus, and the drop across diode is plus minus. Okay, so that's what we need. So this way you can do any circuit. Now you know it, you did it yourself. I mean, at least you told me the voltage, so that is good. Alright, so let's take another one, Clumper. So I will close Clumper. I have drawn this circuit just after the class today. So you can, I have shown you how to draw one circuit, so you can draw the same way. Okay, so here is a Clumper, and I have to give the value of capacitor. So you right click and you write mu. You may not get in the computer, so you put u. It will take it as mu. Okay, mu means microfarad. In the lab usually we use capacitors. Maximum value of capacitor that you use in the lab is 10 microfarad. Mostly we use smaller values. So I have taken 1 micro because this is a value which you can get in the lab. And this is another silicon diode which I have chosen. Here is a 3 volt and I am giving a 5 volt peak to peak, 5 volt peak sine wave. Now tell me what will be the output if you analyze this circuit. So you should tell me first what is the polarity and magnitude of the voltage on the capacitor. When the diode is getting forward bias, it will charge. When does the diode get forward bias? 3 plus 0.7 or something. I don't know what is the cut-in voltage of this diode. Depending upon that, you need to add that with 3. Above that, that the diode get forward biased, and this peak will go beyond that. So whatever is the difference in the two side, that is the voltage to which the capacitor will get charged, with a plus on the left side and minus on the right side. Okay, maybe if it is 0.7 here, maybe 1.3 volt it will get charged. If it is 0.6, 1.4 will be the voltage across the capacitor. And if it is 1.4, then the output voltage is basically 1.4 volt will be subtracted from the input, so it will be clamping downward. Okay, voltage is shifted downward. The waveform will go down by 1.4 volt, which is the voltage on the capacitor. So let's see this. So let's see the input. It's a 5 volt peak sine wave, 3 cycles, because I have shown the stop time of simulation as 3 seconds, and then the output is taken from here. Okay, so if you look at here, you can see, let me maximize it, 5, and this is where this is 3 point something like 3.4. so 5 minus 3.4, 1.6. so roughly 1.6 volt is the capacitor voltage to which it is charged. So if you want to shift more downward, and you can see there is a transient here, this will only happen at the beginning, that's the transient period, but when you come into the steady state, it is a perfect oscillation. So sometimes it may take few cycles, but here in one cycle everything is sorted out, and then now the transient will also depends upon the capacitor value and etc. How long you need to wait, etc. That depends on the component values, like in this case the capacitor value. Okay, so let's try to make this voltage negative. What would happen if I take minus 3? So this may be more interesting. How much it will be clamped, in which direction it will be clamped? Can anybody tell me how much the input voltage will be shifted, and whether it is shifted upward or downward if I take it as minus 3 volt? So minus 3 means I am just changing the polarity. I'm putting the battery upside down. Okay, so I don't need to change the connection, but put a negative sign there. So can you tell me the direction of shift, whether it will shift downward or upward, and what is the amount of shift that you expect? Anybody? Will it be upward or downward?
So downward maybe.
Yes, downward, correct. And how much it will be shifted roughly? Exact value will depend upon the cut-in voltage. If you take it as an ideal diode, can you tell me how much it will be shifted? It will be shifted by the amount of voltage on the capacitor. So you need to tell me how much is the voltage on the capacitor. Earlier it was around 1.5. Now it will be the diode will be forward biased when the input voltage is minus 2.4, right? Minus 2.4 onwards the capacitor will get charged, so it will get charged to 5 plus 2.4, around 7 volt it will get charged, 7 plus volt. So that much it will have to shift downward. Okay, so if you look at the shift from plus 5, it has gone to minus 2.4, right? Minus 2.4. So 0.6 is roughly the cut-in voltage. So the capacitor, this difference is the voltage on the capacitor. In the steady state region, the difference between the two waveform, that should be same everywhere. Any vertical line you take, you measure the voltage of both and find the difference. Now you can you see there is an xy coordinate here. Here if you look at x is equal to 0, y equal to minus 14. So if you, depending upon where you put the cursor, you can find it. So we need y value difference. So y value here it is 5, that we know already. And what we need to know is what is the y value here. It is minus 2.76. So 5 minus minus, that means 5 plus, so that is 7.7. 7.7 is the voltage on the capacitor, with plus on the negative side, minus on the positive side. Hope this is clear to you. So you need to do all of this and prepare a report on all this, whatever I am showing. Prepare a report on all of this and keep it as a record, and when you come to the college you have to submit it. So that will give rise to your internal marks, which is out of 40, plus your attendance in the lab, attendance plus your record of experiments. Okay, so let's take the last one, which we have seen is voltage doubler. To save time, I have just wired up beforehand. Okay, so this is our same circuit which we did. We are giving a sine wave, and I am giving a frequency of the sine wave as 1 Hz, but I am simulating for 10 seconds, which means 10 cycles, and there's a reason why I do that. I have seen that some amount of transient coming, and in order to reach the steady state it takes some amount of time. Okay, so let's run it. And there are a lot of helps available in YouTube. So this is the plot of 10 cycles of the input waveform. Now you should also see the output of the first block, or let's see the final output. So voltage doubler, as I told you, at the steady state it should be 2 Vp. What is Vp? Vp is 5. 2 Vp means 10. So minus 10 it should ultimately get it. But it gradually reaches there because of the transient part. Okay, but steady state, once it reaches after a few cycles, then it remains there without any change. So I think I have shown you this sort of thing. And this is happening because the input voltage and the charge on the capacitor. So if I plot this voltage, you can see that. So whenever the input voltage go below the blue line also follows it. But when it goes up, the blue line will not respond because the diode D2 will be reverse biased. But in the next cycle again, the red line goes below the blue line, so the blue line will follow it because the diode will be forward biased for a short time. So whenever the red line goes below the blue line, the diode D2 is forward biased, and initially it is forward biased for longer time and then lesser. So only during the peak there is a slight time. Still it has not reached, after 10 cycle also it has not completely reached the final value. Still some amount of transient is left. And can you tell me whether it will reach exactly minus 10 volt or not? What I explained in the class is with ideal diodes, okay, but here it is not ideal diode, it's a real diode. So with the real diode, it has got a cut-in voltage, so there will be a drop across it, and therefore it will not reach minus 2 Vp. It will be slightly lesser than that. The steady state value will be slightly less than minus 10 volt. That's because we are using whatever we simulate, that is with real components. It's a model of the real component. So, and if you look at the current flowing through the diode, you will see that whenever it is forward bias, there is a small current, okay, only during the forward bias. So see, this is the current waveform. The current is becoming smaller and smaller because the duration for which it is forward biased is very small. So lots of details you can see here, and it's very easy, very convenient, just like Logisim for the last semester. If you just sit with it and wire up whatever you learn in the class, you will understand things very well. If you don't do this, gradually you may lose interest. Okay, any questions?
So what is the voltage across B1?
Voltage across D1, this one I have already plotted. So that is voltage across D1 is the red one. First, green is basically the input voltage, blue is the output voltage, red is the voltage across D1, and what I plotted finally, these peaks, these are corresponding to the current through D2. Okay, current through D2. So it's, you can see that I D2. So D2, this current. If you want, you can plot D1 current also. So that is the purple one, ID1. Okay, so shall we stop here?